Good morning, everyone. I trust you had a pleasant long weekend. I hope you did anyway. We are beginning on something that's a little bit new today. And the big heading that we put on this topic that we're about to start today is transient analysis. And that's not language that most of us use all the time, the idea of something transient. Some people maybe do, but I don't think I use that word much except for in the context of talking about engineering type stuff. And so what I figured I would do is kind of first explain what do we kind of mean by transient analysis. So the idea of something that is transient is something that changes over a kind of specified period of time, but then reaches a new normal. Okay, that's kind of the big idea behind the word transient, is that there's a period of change, but that it will trend towards some new normal. Okay, so that's kind of a big, broad definition of the word transient. When it comes to what we're talking about in circuits, this happens as a result, or the fact that we get transients is a result that we've introduced these two new circuit components that, one of them's an inductor and one of them's a capacitor. And these two new circuit components actually have a time dependency that's built into them in their relationship between voltage and current. Okay? And because there's this time dependency between voltage and current, this is where essentially non-instantaneous behavior starts to come into our circuits. Okay? Now, how does it work in terms of the mathematics of it? Well, you can see here, and I guess I'm going to contrast it with resistors over here, right? If you're talking about resistors, there is no time dependency between voltage and current, right? If you know the voltage, then right at that instant in time, you also know the current if you know the resistance value. So there's no kind of time dependency. There's instantaneous response in a resistor. If you change the voltage, the current is going to change instantaneously. Or if you change the current, the voltage is going to change instantaneously. But you see with inductors and with capacitors, if you make a change, let's say in a current value, right, then what you really have is that it's the time rate of change of current that affects the voltage across that inductor, right? So there's this time element that has come in when you look at the relationship between voltage and current in an inductor, right? The same is true for the relationship between voltage and current and capacitors. What you see in that case is that if you were to take sort of the area under the curve of current, right, and multiply it by some constant that has to do with the capacitor, 1 over that constant really, right, that's going to be equal to a change in the amount of voltage, okay? So, but in either of these cases, we see this time-dependent relationship between voltage and current. And because we have that, that's what leads to the idea that there is not an instantaneous, I really should back up a second, there's not a complete instantaneous response that happens once you change one of our electrical parameters like voltage or current, okay? So what are the things that might cause there to be some kind of an instantaneous change? Well, there's sort of two categories that we can look at. One of them is you can talk about a switch being turned on or turned off, or some other kinds of switches might even turn to where they connect in one position and then an instant in time, they switch over to another position, okay? So when switches change in a circuit, that is usually an indicator that there was some kind of an instantaneous change that happened in the circuit. And then from that point on, we can analyze how the circuit will respond in terms of voltages and currents to that instantaneous change in the nature of the circuit, okay? There's another category as well that I don't think we have as many examples of this like in your homework and such, but you can also set up a time-dependent source, right? And you can set up a time-dependent source so that it, let's say, starts off at 0 volts. Let's say it's a voltage source. Starts out at 0 volts. And then at some point in time, you could define that voltage source that it turns on and then stays at that level at some, you could even do that for some period of time and then turn it back off, right? So we can do time-dependent sources as well, and it's not hard for us to define what an instantaneous change might be in a time-dependent source, okay? But these are kind of the two big categories of where we might see some kind of an instantaneous change going on inside of a circuit. One other term that I want to identify here fairly soon is this idea of being a steady state, okay? And one of the code bits of language that you're going to see in some of your problems is the phrase, for a long time, okay? The idea behind that is that usually when you flip a switch or when you change the state of a source, there will be some, kind of a process through which all of these parameters change, but like I mentioned before, they will tend to approach some kind of a new steady state. That's why we call it steady state. I guess it's bad to define a term in terms of itself, but that's what I'm trying to get at, is that there is some new set of values that circuit is going to assume eventually. Once all this time-dependent behavior has completed, it will reach some new normal, right, as a result of some instantaneous change, okay? And when we're talking about transient analysis, what we're trying to do is first kind of characterize generally how do these transient behaviors work, and then if we can do even better than that, we'd like to define how we can describe them mathematically. In other words, can we come up with functions that might be functions of time that would give us voltages or currents as a function of time, and that way we would know sort of what a curve would look like if we wanted to have one of those to say, here's what the curve would look like for voltage, or here's what the curve would look like for current as a function of time. Okay, so I wanted to give some general notes here right at the beginning to sort of talk about what we're getting into with this transient analysis. I will mention this as well. As of right now, we are going to be talking about transient analysis in DC circuits. Okay, that means that we are not setting up sources that are designed to sort of change continuously over time. The big example of that might be sinusoidal sources. Okay, now it's not that transient effects don't exist in sinusoidal, kind of AC kind of problems, but that's not what we're talking about right now. We're talking about DC effects like this, and the truth is, in this particular course, we don't really get into transient effects in AC circuits just yet. Okay, so maybe count that as a blessing, or maybe you're disappointed, I don't know, but that's kind of setting up the scope of what we're trying to do in this course, and then kind of for right now also. All right, well, let's get into when we're talking about these DC circuits, how do we go about trying to do one of these transient analysis? Often, the first thing that we have to do is identify what we are going to have as our steady states, right? And usually if there's at least one change that happens over time, that generally means there are at least two states that you are talking about of that circuit. If there's one change, that's probably going to be two states, meaning the state that you had been in, and then once the change occurs, there is a state that you will start to approach for that circuit. And what I want to do is give you some rules on how you can come up with what these steady states are. And this is important before we get into even the more nitty-gritty of how does it look as it changes from one steady state to the new steady state through that transient period of time. Okay? So here's the first one. If you have a circuit that consists of DC sources, that can be dependent or independent sources, it can be voltage sources or current sources, right? But if you have a circuit consisting of DC sources, resistors, capacitors, inductors, and switches, and if you leave your switches in a particular state, in other words, you're not allowing any changes to switches, or maybe I should expand that a little bit and also say you're not going to allow any changes like a time-dependent source for a long period of time. If that occurs and you go a long period of time, then over that period of time, your inductors will behave as though they are short circuits. What does that mean? Okay, just a wire. Now, if you think about this, this kind of makes sense with respect to the effect that we described in inductors. They are basically already a wire. They're just wound around a whole bunch of times so that they can create a big magnetic field. Well, the thing is, that magnetic field will just stay in whatever state it's in if a constant current keeps flowing, right? And so there's really kind of, once you've either built up that magnetic field or it depletes, there's not any sort of further action of that element other than just being a conductor. Okay, so that's what we see with inductors, is that they are going to behave like short circuits if they are connected for a long period of time. Last note I'm going to make on that is we are assuming, both for the inductors and the capacitors I'm going to get to in just a second, we are assuming that they are ideal. In other words, we're not dealing with the fact that a lot of real inductors also bring along with it some amount of resistance. For now, we're going to kind of treat it as though we can somehow get an ideal inductor. All right? For capacitors, if you leave them connected for a long period of time into a circuit where there's no changes going on, they will begin to behave like open circuits. And if you think about the construction of a capacitor, that also makes sense. What is it that you have between the two terminals of a capacitor? The terminals usually connect to something like big plates or something like that, but then what's in between the plates? Okay? You usually have some kind of an insulator between the plates. And so for a capacitor, if you just leave them connected for a long period of time, any sort of time-dependent effects will go away and the capacitor will start to look like an open circuit if you leave it connected for a long period of time. So these two rules, that inductors will start to look like short circuits, meaning kind of like just a wire, and capacitors will start to look like open circuits, meaning no connection at all, if you leave them connected into a DC circuit with no changes happening. These two effects can be used for us to do what's called a steady state analysis of our circuits and kind of figure out what are the two states, the one that we had been in for a long period of time, and then we make a change, and then the second state is which one are we trying to trend toward now that we've made this change. Okay? And so that's kind of the third bullet there. Steady state behavior can be determined by applying those kinds of substitutions, either short circuit or open circuit, depending on what kind of element you've got, and then using whatever circuit analysis technique we would like to use to figure out what we want to know in the rest of the circuit. Okay? And I just made a list of them down there. That's sometimes helpful to do to kind of think through all the stuff that we've talked about already, right? We certainly have what I would say that are the big three, and most everything else stems out of the big three, but that is Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. But then out of those essential principles come things like voltage or current division, equivalent resistance, practical source transformation, nodal and mesh analysis, superposition, Thevenin and Norton equivalence. All this stuff basically stems out of those original that I mentioned. But any one of these techniques can be used once you apply those substitutions, and that's how we do these steady state analysis kind of approaches. Okay, so shall we do an example of that real quick? Knew you would want to. So here's an example. There's a circuit you see right there, and it says here, nothing had changed in this circuit for a long time. There you see that code word, or code phrase, right? For a long time, right? That means that any transient effects that may have been present in the circuit, they are all gone, and so we can treat our inductors like short circuits and our capacitors like open circuits. Then, suddenly, at time t equals 0, the switch states change as shown, and then nothing else changes again after that. So where are my switch states? Okay, I've got 3 switches here, and I should probably talk through what these switch states mean. The symbol for a switch is kind of this little kind of leg that's open right there, and this says that at time t equals 0, this switch will close, meaning that for all that time up until time equals 0, that switch was open. Does that make sense? That first switch there on the left. What about these 2 switches over on the right? How do those work, you think? They had been closed for all this period of time, these 2 switches over here on the right. They'd been closed for all this period of time, and at time t equals 0, they open. Okay, meaning that after time 0, current is no longer allowed to flow across those connection points. Or I guess they were connection points, and now they no longer are. Okay? All right. So nothing changes after that. It says find each of the parameters below A right before the switches change. Okay, the way that we denote that oftentimes in our kind of shorthand of that is time t equals 0 minus. Okay, anytime you have instantaneous changes, that creates a bit of difficulty in describing functions and such, and so that's probably some notation that you learned in math class where you could do like at some point in time, but then put a little note next to it and say, yeah, but right before that. Or you could do time t equals 0 plus. What does that mean? It means like right after you make that change, or right after that point in time. Okay? And then part B says a long time after the switches change. Okay? And the way that we can denote that is time approaching infinity. Okay? So far so good? Okay, so how do you want to start with this problem? Okay? How about this? Because we know we can do some substitutions, right? We're dealing with two steady states of this circuit. And when it's in steady state, what we can do is we can treat inductors like short circuits and capacitors like open circuits. So I propose that we sort of identify for before time 0 what was the steady state of this circuit, and then at time t equal infinity or approaching infinity, what will the new steady state of this circuit be like? So I'm going to label those up here at the top and say, time, okay, equals 0 minus. And I'm going to do that over here on the left. And over on the right, we're going to have time approaching infinity. What does the circuit look like on the left case? I'm going to redraw it, okay? What we see there is that we're going to have a current source. That doesn't change, 2 amps. Then what does it connect to? How does that inductor look, that 10 millihenry inductor? It's like it's not there. It's like it's just a wire. So I can kind of just ignore it and pretend like there is a path for current to flow right there, because there is, but I'm not going to draw the inductor. So here I'm going to have a 100 ohm resistor. Okay? Now when we are before time 0, how do I handle this switch for that next little leg of this circuit? Okay? Because that switch was open prior to time equals 0, there's no place for current to flow. And since there's no current flowing, it's kind of like that 10 ohm resistor sort of just dangling off of there, but there's no way current can flow in it because the switch is open, right? So we can just not draw it. It's like it's not there. Okay? What about the 5 volt source? Okay, it's still there. So we're kind of finished there with the left side of the circuit. What happens over here on the right side of the circuit? Before time equals 0, both of these switches were closed, right? So I'll tell you what, I'm going to go way over here to the right and do that one first. Since it was closed, it's like it's going through this 200 ohm resistor, right? And from there, that switch up at the top was also closed at time 0 minus and earlier, right? So I'm going to treat that like it's closed. How do I treat my little capacitor there, my 10 millifarad capacitor? It's open, meaning there's no connection. So that means the only other thing I have is this little leg that would be my 20 ohm resistor that would be connected something like that. Now, I could write the 20 ohm on there if I wanted, but many of you are looking at that going, would that even do anything? Okay. Some of you say, nope, that doesn't look like it would do anything. Why not? That's a short circuit, right? The two ends of that resistor are connected to the same node. And because they're connected to the same node, that's essentially 0 resistance for that path on the upper side of it. And if there's 0 resistance path, how much current will flow on the path that is non-zero resistance? None, right? So since no current will flow on the 20 ohm resistor in that case, we can eliminate it. And our circuit that we have becomes that. Okay, that's what the equivalent circuit is. And in terms of finding what things like voltages and currents are, right at time equals 0 minus, right before the switches change. Now, while we're on a roll here, let's go ahead and draw what it looks like once t starts to approach infinity. Okay? How do you handle that? Same type of process, right? We're still going to treat all of our inductors as short circuits and all of our capacitors as open circuits, but now we have a different set of switch states that we have to take care of because the switch has changed, right? So now we have to figure out what those are going to be a long time from now. So what we'll have is the 2 amp source there. It's going to now be going across this 100 ohm resistor here. But then there's going to be another resistor over here that is a 10 ohm resistor, and it now is in the game because once time starts to go to infinity, that switch is closed for all that time. That left switch is closed, right? So that's now participating in all of this. And then we go over here where we've got a 5 volt source still. And now this leg of the circuit essentially stops where that switch is. We have another leg of the circuit that is this 20 ohm. It connects up in here like this. And I'm just going to show gaps in the circuit where the switches were. Then we're going to have our 200 ohm resistor here. But then there's a gap there also because there's an open circuit at that location. With me so far? So that's my 200 ohm over there. So here's a question for you. How much current can flow on this circuit over here? Okay? There is no path anymore for current to keep flowing over there. We'll use that here in just a minute whenever we start getting ready to analyze that circuit. Okay? So this is kind of our first step when we're doing one of these steady state analyses. It's a good idea to actually go ahead and redraw the circuit, you know, at each of your states. Usually there's one that for a long time it's been a particular state, and so it's going to be that right before something changes, and then it's going to reach a new steady state if you let it go on into time equal infinity or approaching infinity. Okay? So we drew the 2 states. Now what? Maybe it's a good idea to identify what we're looking for, right? It says there we're trying to figure out the current through the inductor and the voltage across the capacitor. Okay? And we're supposed to do that right before the switches change and then a long time after the switches change. Okay? So why don't we start over here on the inductor side. Okay? So I'll do the inductor before and after the change. On the left circuit, is there a current that I can identify? You know, the inductor's not there anymore, right? But is there a current I can identify that would be the current through the inductor? Okay? It would be this one right here, right? I can identify a current, and I'll just, I guess I'll show it as being down like this. So this is basically, I'll call it I sub L at 0 minus. If you kind of show it like a function, that's a nice way to do it. How do I figure that out? Okay, I can solve for it. What's a good technique for solving for it? Okay, I do like source transformation. What do I like about source transformation? Okay, yeah, I mean, it's pretty easy to do for one thing, and we can turn this circuit into something that might be easier for us to deal with if we do that. Okay, one way of doing that is we can actually transform the current source with the resistor that's over there on the left into a voltage source in series with a resistor. Okay, so I can say this will become a voltage source in series with a 100 ohm resistor, and that will connect up into the rest of my circuit like this, where that's a 200 ohm. And The only other thing that I've got to do there to make that valid is pick the right value for my voltage source. How do I do that? I have a current and I have a resistance. You just take that current of 2 amps times the resistance of 100 ohms, and that gives you a new voltage, right? So 2 amps times 100 ohms equals 200 volts. So now I have that. Once I have a 200 volt resistance in series with a 100 ohm resistor, in series with a 5 volt source, in series with a 200 ohm resistance, what is this circuit essentially? One loop, right? And so if I want to, I could do a loop, a sum of voltages around this loop in terms of I, right? So let me go ahead and identify here a different I. I'll just call it plain old I. What's that I value going to be around this loop? Well, we can find it by summing voltages, right? I can take minus 200 volts plus the voltage across the 100 ohm resistor is going to be 100 ohms times what? I. Then I'll have plus 5 volts, and then I will have plus 200 ohms times I. And all that has to be equal to 0. I can solve that for I. So when I do that, I becomes 0.65 amps. Okay, now why does that help me? Or maybe it doesn't, but do you think that might help me? I think so. Okay, here's why I think so. That was an I that was flowing around this loop. That's the same I that would be flowing right here as well. Okay, now when we take it back to our original circuit, we see that there is no longer just a series circuit. It has a place where current can split right there, right? Could I do a KCL equation right there? Okay, how do I do that? Well, I think the easiest way is to notice that there's 2 amps going here, right? There's I coming in here, and I just figured out what I was. And then I've got I sub L that's coming in from, downward from above up there. So I should be able to sum this up. We'll take exiting as positive, all right? So I will have 2 amps exiting minus I sub L at time 0 minus 0.65 amps. And that's equal to 0. So what is my current in my inductor right before the switches change? Okay, should be 1.35 amps. And it is actually important here to keep in mind, so I'm going to call it out real quick here. It's good to keep in mind that I assumed a direction for that current going through that inductor. I then used that assumed direction to solve through, and I came up with a positive number. What does that positive number mean? It means that direction I assumed at the beginning is correct. Okay, if I had done all that and come up with a negative number, what does that mean? It's really the opposite of the way I had assumed initially. Okay, so it looks like we just finished coming up with the current through the inductor before the switches changed. Right at the instant before the switches changed, we now know what the current is going through the inductor, 1.35 amps. How do I figure out what the current is in the inductor after the switches flip? Okay, same type of approach, but now the circuit's a little bit different. So let me go ahead and flip over to the other diagram over here. When we let time go to infinity, right, we're trying to figure out what this new steady state is going off into infinity. Let me ask this. Does it matter that I've got all this junk over here to the right? There's no place for current to go, so none of that even matters to me. What does matter? what I have on the left, now where is the current that I care about? Through this inductor, so I'm going to define it the same direction again. This is going to be I sub L at infinity. Okay, how do I figure that out? Current division. Perfect textbook case of current division, right? I know how much current is flowing. There's only two paths for the current to go. The 100 ohm resistor and the 10 ohm resistor, right? So this is a perfect setup to be able to use current division. How do you use current division? You take the total current, which in this case is 2 amps, and multiply by what? Okay, it's a ratio where in the denominator it's the sum of the two resistances, right? 100 ohms plus 10 ohms. What do I put in the numerator to get just the current on the 100 ohm leg? I want to use the opposite one for current division, right? So I put 10 ohms in the numerator. Okay? And so what we came up with there is the current that you are going to have in the inductor if you let it, you know, the circuit stay undisturbed for an infinite amount of time. You will eventually end up at how much current in that inductor. I came out here with, tell you what, I'm just going to punch it in real quick. We've got 2 times 10 over 100 plus 10. 0.1818 repeating. Okay? So if you look at what we were supposed to find, we basically figured out, this is the answer down here. The first one we did is the answer to question 1A. This is the answer to question 1B, right? Essentially before and after the steady state conditions. Okay, what now? So keep in mind, the circuits are not going to change. I had my 2 different circuits that I drew right there. What it looks like before, you know, right before the switches flip, and then what it's going to look like at time equal infinity. Okay. What we need to do here is probably figure out, is there an element across which the voltage in the capacitor would be the same as the voltage in that element? Does that make sense? So if you look up here, we basically have that this capacitor goes on this node over to what other node? Now, since these switches open over there, what does that do? Okay, I think what I'm looking at over here is that this would be my yellow node, and then down here, this would be my blue node. Okay, now here's a question. How much voltage drops in this time approaching infinity? How much voltage drops on the 20 ohm resistor? Might be a tricky question. Okay. Is there any path for current to flow? Nope. So how much voltage drops on the 20 ohm resistor? All of it. Well, that's not a good answer. 0. No voltage drops. Sorry, you sounded convincing to me, so I went with you. All right, no voltage drops on there. That means that whatever voltage I have over here is also the voltage that I have over, you know, where the capacitor voltage is actually. Does that make sense? Matter of fact, all of that stuff is going to be at the same voltage in this state because there's no place for current to flow. So if I can just find the voltage anywhere over there, then I'm good to go. So what does that mean I have to do? Okay, I'll tell you what, I'm going to draw this circuit even just a little bit different, right, where I've got my 2 amp here going through my 100 ohm and through my 10 ohm, and then going across my 5 volt. But everything after that, since no current flows, I don't care. And this is also going to be my VC voltage. because there's no current that flows over there. That's what I'm trying to drive at. Okay, so let me ask you this. Can we figure out what that voltage is, VC over there? We can. Probably the easiest way, at least in my mind, to do this is to remember that we really haven't changed anything, and we know the current flowing through this resistor. What was that current? 0.1818 amps. If I know the current flowing through that resistor, what's the voltage across that resistor? Okay, it's just going to be that current times the resistance, right? So that voltage is going to be equal to 0.1818 amps times 100 ohms, right? And what's that going to be? 18.18 volts. Okay, that's the voltage from the bottom terminal down there up to the top terminal. And we've got this big parallel circuit. Let me ask you this. Can I do a voltage loop essentially around here? Is that acceptable? Okay. Well, I'm about to do it, so speak now or forever hold your peace. All right. So we're going to do minus 18.18 volts. Okay. We come up to the 5 volt source, so we do plus 5 volts. What else? Plus VC. So what is VC? Okay. 13.18 volts. And this is, if I want to kind of denote it even better, this is the voltage in the capacitor at time infinity. And that is the answer to question 2B. Some of you might be going crazy because I went out of order a little bit. So sorry. Okay. Now what about the question over here that we had the voltage, the voltage across the capacitor before we flip the switches? Okay. That would be the left circuit. When we, in the state and time before we flip the switches, do we have a circuit element that has the same voltage across it as the capacitor? Notice here how when these switches are closed, which is what it is at times 0 and earlier, right? 0 minus and earlier, the 200 ohm resistor connects across the same 2 nodes as the capacitor. So whatever voltage I have on the 200 ohm resistor is going to be the voltage that I have on the capacitor, right? So that means I can carry forward, even though I've eliminated the capacitor, whatever voltage I get on this 200 ohm resistor, that's the voltage I'm looking for. Is that easy to find? Sure is. Why? Okay. I actually already know this current is 0.65 amps. So this voltage here, right, that voltage I'm going to call V sub C again. That voltage is just going to be equal to, and this is V sub C, by the way, at 0 minus. It's just going to be equal to 0.65 amps times what? 200 ohms. So let me punch that in. Okay, that would be 130 volts. And that's the answer to question 2A. Okay, so we did it. May not have been pretty, but we got through it, right? We figured out what were these steady state conditions going to be for this circuit. And we did it just by doing substitutions for our capacitor and for our inductor, right? Capacitor acts like an open circuit. Inductor acts like a short circuit. And you just analyze it using whatever circuit analysis tools come to your mind, as long as they're valid, right? Use whatever you want to figure out what these values are. Maybe the trickiest part is being able to look and determine, like in this one that we just did, right? I determined that the voltage across the capacitor was going to be the same as the 200 ohm resistor. That may be one of the trickiest parts, is to kind of figure out, once you've eliminated your inductors and your capacitors, can you find some other thing in the circuit that would have the same voltage or current, whichever you're looking for, right, as what it is that you're looking for. Okay, questions? All right, I have something even more exciting for you. And I can see the anticipation on your faces. We can do better than just figuring out what the steady state conditions are for these circuits.